Okay, thank you, Professor Soiresh, for your kind words. I also have many fond memories with you, and yeah, I am in contact with you. So, very good afternoon to all the participants and organizers. First of all, I would like to thank the organizers for inviting me in this e-workshop on spectroscopic technique, basic and application. Yeah, please. Just a moment here. Sorry. Yeah, just a moment. Is it now okay? Okay. Okay. So, since morning we have listened to some wonderful talks by eminent speakers like Professor D.D. Sharma and Vasant Sathe and also Professor Prabhu. Now, what I would like to do in this talk is to present some of related to the designing of p-type transparent conducting oxides, and these are wide bandgap transparent conducting oxides material, and how to probe the valence band and through X-ray photoelectron spectroscopy as well as to support by density functional theory. I will also like to study the valence band dispersion by Raman spectroscopy, although that I have not mentioned in the title. But depending on the time available, I will touch some few aspects of this p-type transparent conducting oxides. So specifically, the layout of this talk will be something like this. At first, I very briefly introduce to TCO, as I have been informed by the organizers that there will be some master degree students and young research scholars. So I will very briefly introduce, and then I shall mention about the current bottleneck of the p-type TCO and how to overcome this current bottleneck. And then specifically, I shall mention about the copper Delafosside system as potential PTCO. And then I shall touch upon that some spectroscopic technique for this valence band dispersion evaluation, and whether we have got really some interesting result to overcome this conductivity bottleneck. And then, depending on time, as I said, I shall touch upon another two aspects, that is the, whole delocalization probe by Raman spectroscopy and also emergence of negative capacitance in such of this system. So, let me just first tell a few lines about transparent conducting oxides. As you know, that electrical conductivity and optical transparency, these are two mutually exclusive properties. It is well known that materials which are optically transparent, like glass, they are not electrically conducting, and metals, all the students know that it is electrically conducting but optically not transparent. Now, effort to bring these two properties in a single material is not new. More than 100 years ago, cadmium oxide was synthesized, and this primitive result was, of course, the material was transparent and conducting, but the results are not reproducible, and also, cadmium is carcinogenic. So, the real breakthrough came in the 50s of the last century when this indium doped tin oxide was developed. This material is popularly known as ITO and known to everybody, and it is the ubiquitous substrate for many optoelectronic applications, for example, flat panel display, solar cell, organic light emitting diode, and many more. Now, since then, a large number of other systems have been developed. For example, I mentioned a few: tin oxide with different kind of doping, zinc oxide with different kind of doping, indium oxide, and some ternaries like zinc stannate, zinc stannic, gallium indium oxide, silver indium oxide, magnesium indium oxide, and so on. And now also many new systems are coming. Now, I already mentioned the applications starting from solar cells, smart window, flat panel display, touch panel, light emitting diode, heat reflector, and many more. Now, if you just notice carefully that what is the role played by these transparent conducting oxides in such applications, you can find there are twofold roles. The first one is to allow the visible photon to pass through so that it can reach the junction. And secondly, if it is a device, then the photo generated carrier that you have to collect, and so that it provides some low resistive path. So these are the two, role played by the transparent conducting oxides. But the so-called active device fabrication out of this TCO is not achieved. Now, the question is that why it is very difficult to get active device. The passive applications are okay, there are many, but active device application out of this all transparent oxide material are so far elusive. Now, before answering the question that where is the difficulty, let me just tell you that why people are interested to get active devices out of, for example, this oxide exclusive material. Now, there is a famous article in Nature by Gordon Moore about a few years ago, and the title of the paper was that Emergence of Transparent Electronics. And there he discussed many possibilities, okay, about this oxide electronics if it is possible. I just mentioned a few of them. For example, functional windows. And for example, you can replace all the window panes of any houses by this transparent junction. Then it will not only allow the visible portion of the light to come into your room, but whatever small portion of UV part in the solar spectrum, using that you can generate some power. Also, the future mobile phone, as you can see, that this will look like just a piece of glass or a piece of plastic. Future computer may look like this one, and there are many exotic application like defense people are very much interested to have this one. You can replace your spectacle glass by all transparent junction, so that again it will not only protect your eyes from the UV part of the solar spectrum, but you can generate some power so that in future maybe you can charge your mobile phone by some simple devices maybe. Also, invisible circuit, as these are wide bandgap semiconductors, so you can fabricate LED and laser. So there are many application possibilities. So that is the reason why people are interested to get this all oxide exclusive electronic system. But then what is the main difficulty? The answer is basically if we have if you have noticed that the oxide system that I have mentioned so far, they are all electrically N-type in nature. That means the electrons are the majority carrier. Now, why it is then very difficult to have the P-type wide bandgap semiconductor? The answer is basically related with the band structure. Now, you know that in this transparent conducting oxides, the valence band is composed of oxygen p orbital. Just if you look at this cartoon, you can see that these are the p lobes, and these actually constitute the valence band. On the other hand, the conduction band is composed of this s orbital, metal s orbital, which are larger volume and they are spherically symmetric. So what happens that suppose somehow you could generate electron by say donor level, then the electron they can move very easily, okay, at some small electric field within this very large space of the conduction band. So N-type doping is not a problem. But what happens that when you generate some holes somehow, for example by suitable doping, then the hole must be confined within this oxygen p orbital, because they are actually the constituent of valence band. So there you can find that the curvature is large, space is limited. So in other words, you need large electric field to move them. So that means in physics world we can say that it has large effective mass. So this is why in p-type oxide material, achievement of higher mobility is extremely difficult. Also, the valence band maxima is so deep so that it's difficult to get shallow acceptor level. So these are the reasons why it is not possible, till so far, not efficient p-type PCO is not achieved. Now the student can ask the question, then why, for example, the elemental semiconductors like silicon or germanium, that can easily be p-type doped? The answer is again can be found in the band structure. As you know, in silicon germanium, both the valence band and the conduction band, they are composed of sp hybridized orbital, and they are both dispersed. So it is you can achieve larger mobilities in such systems. Now, why? Then what is the way out? Before answering this question, just I want to show you from a very recent review article published in Nature Communication, where the authors, they have, you see the plotted the number of compound with effective mass. You see that at the low effective mass region, all the compounds are having electrons at the majority carrier. You see the blue lines all having electrons as majority carrier. But this red line, you can see that also the number of compounds is very small, and even the effective mass is much larger. Okay. Also, if you look at this, lower, plot, you can find that these are the all materials, they are N-type conducting, but these are the current P-type conducting materials. You can see there are three, prototype. One is the copper aluminum oxide, another is strontium copper oxide, another is zinc rhodium oxide. But look that all of them having much larger effective mass, greater than 2, again indicating that mobility will be difficult to achieve. So then what is the way out? The way out is that, as you have seen, that the valence band is basically spatially confined from oxygen p orbital. So we have to engineer the valence band. We have to disperse the valence band. How we can do that? This is a technique which is called the orbital alloying technique. That means we have to find out some element which will be having some orbital which is having equivalent energy with oxygen p orbital, and then if we can alloy this orbital, then we will be able to disperse the valence band. We will be able to create a larger volume of the valence band, you can say, and then if we can introduce some doping, then the holes will having enough space so that under the application of small electric field, it can move easily, or on the other hand, we can expect to decrease the effective mass. So this is so-called orbital alloying technique or chemical modulation of valence band technique. And it is found that copper 3d orbital or silver 4d orbital, they match this criteria. So you can alloy the orbital of this oxygen p with copper 3d or silver 4d to get some compound of suitable nature. Some people suggest that this transition metal like this iron, they are also having some orbital having similar energy with that of oxygen p. But the problem there is some DD transition, and coloration is produced in the visible part, so that that is detrimental for transparent devices. So that will not do. So these are the two materials that is has to be looked. And based on this criteria, a large number of systems. The prototype is copper aluminum oxide, and which is having band gap 3.5 electron volt, and then copper gallium oxide. So these are basically the Delafoe site of structure with general structure AbO2. And you have the doping possibilities both at A site and B site, and large number of compound can be synthesized. And the major criteria is that the band gap should be greater than 3.1 electron volt, so that it become transparent. It remains transparent in the visible region. And when this was suggested, and so we also we are working on this material for more than 2 decades. And initially, the phase formation was itself a challenge, because this ternary system, their stoichiometry mentioned the correct phase formation itself a challenge, and also the thin film fabrication. But we overcome all this problem, and this is a 3-target magnetron sputtering system in our lab. And also we use the RF magnetron sputtering. I am not discussing the technique, but the correct phase formation in the thin film form have been achieved. And we published a large number of papers, I mean, in covering various aspects, for example, size-dependent electrical property, optical property, okay, and these are our, some of our relevant publications, and these are the optical, electrical properties, and skipping all these things, just mainly just mention one thing about this one, that these delaphocytes are good for thermoelectric application also. Why? Because if you look at the thermoelectric figure of merit, it is well known that to achieve higher ZT, that is figure of merit, you should increase sigma, that is electrical conductivity. At the same time, you should decrease the thermal conductivity. But you know that they are not independent. They are basically dependent. And if you increase sigma, essentially it will lead to increase of K by Weidmann-Franch law, and ZT remain constant. So that's why there was a proposition by Higgs where he suggested that if you can find some system where you have independent control of sigma and K, then it is possible to obtain higher ZT. Now this delaphocyte class basically satisfy this criteria inherently, because in the AV plane the carrier density is higher and the C-axis is much larger, so that's why you have basically anisotropy in the system, and you have independent variation of sigma and K is possible, and large ZT is of course possible. And we showed that more than 400 microvolt per Kelvin Seebeck coefficient could be achieved in such material. Okay, now also we fabricated the all transparent junction based on doped zinc oxide of N-type material and this oxygen doped copper aluminum oxide, and the device transparency is more than 80%. We reported this result also. But after 1.5 decades of research by our group and also some famous group, for example, the Tokyo Institute of Technology group led by Professor Hosono, it is now evident that there are some inherent, limitation of such system, and the best electrical properties reported of this material still at least 2-3 orders of magnitude lower than that of the best counterpart of N-type material. So what to do? So this is actually the conductivity bottleneck of this P-type TCO. So we thought over this problem, and we thought that it is not sufficient to achieve only valence band dispersion. So even if valence band is dispersed, still it is very difficult to move the hole. The question is why? Actually, the presence of oxygen is itself detrimental, because oxygen, as you all know, is a highly electronegative element. So whenever hole is present, so they face Coulombic attraction, and it's very difficult to move them. You need large electric field to move the hole from the influence of oxygen. So along with the valence band dispersion, if you somehow could decrease the electronegativity of the anionic site, then it will lead to the higher mobility and better electrical properties of this PTCO. So based on this idea, we thought that we will try to dope at anionic site by some less electronegative element. For example, you know that chalcogen, sulfur, selenium, tellurium, they are less electronegative than oxygen, and then we try to replace the sum of the oxygen, that is doping at anionic site, in such system. But as you know, doping at anionic site is not so straightforward. So whether our thinking is right, so that's why we have performed extensive density functional theory based calculation. So what may be the possible outcome to judge? Now, I am not going detail about the techniques. I will just show the published paper later. So then if somebody is interested, that how this is actually performed. He or she can have a look. But very, simply I can say you that, okay, we can do density functional theory based calculation permitted to our system. We can handle more than 120 atoms at a time. So the left panel is basically the pristine copper aluminum oxide. Okay, and the middle panel, you can see here that we have replaced some of the oxygen atom, but by sulfur atom. These yellow atoms are sulfur, and here we have shown oxygen atom replaced by selenium. Actually, we have also calculated some tellurium incorporation in place of oxygen, but I am not showing that result today because that experiment is not yet done. So only the sulfur and selenium doped system at oxygen site, remember. So this is done, and when we optimize the structure, so we could get some interesting result. So basically, the most important thing is that the local symmetry get changed. It is obvious because what happened that as we replace the oxygen by sulfur or selenium, then the bond angle get changed and the local symmetry get changed. So it must have some effect on the band structure. Okay, so because the symmetry and band structure are intimately related, and actually we found that the phase group actually changes from R3 bar M to P3M1. So that means the polytype formation actually took place, and this is the effect of the band structure when these chalcogen were incorporated at the anionic site. I just spent 2 minutes here because the results are very interesting and important, I think. You see, the leftmost panel, this one, this is the band structure of pristine copper aluminum oxide. And look at the number of features. First of all, you see the valence band maxima is not at the same K value at the conduction band minima, that is the gamma point. Okay, you have indirect band gap. So this is first thing. Second one, you see that valence band is basically a flat one, indicating that the holes are heavy. So that means, as we have seen from our simple discussion, qualitative discussion, that hole mobility will be very low. So this is also supported by band structure. Here you have heavy hole, and the density of state at Fermi level is also very low. But as soon as we incorporate some sulfur at the oxygen place, see the middle band structure. It is very interesting how the band structure got changed. You see here at the gamma point, the valence band maxima now comes. So that means essentially the material becomes direct band gap. Not only that, you see that along with the heavy hole band, a large number of light hole bands have also appeared. Okay? So this is very important for getting better electrical properties and higher mobility, as I already indicated. Okay, and also significant increase of the density of state. In tellurium doped system, more or less similar result. Also, it becomes direct band gap, light hole state generates, and also, significant improvement of density of state happened. When you look at the electron localization function plot, ELF plot, you get the same thing. You see, when oxygen is replaced by sulfur, you see this is the region which is oxygen deficient, electron deficient. So that means whole dispersion have been achieved. This is also suggesting for selenium also a similar trend have been achieved. Now, as our DFT is basically predicting that the structure the property will be very interesting, and maybe some of the problem will be solved if we can achieve this anionic site doping. So we try to perform the experiment. Okay, this is also Mulliken charge analysis. Exactly same result as ELF has been obtained. You see here that when we replace oxygen by sulfur, selenium, then the region which is electron deficient, that actually increased, indicating that the valence band dispersion it is more, and the electronegativity have decreased. So that's why electron become deficient in nature. So all these results suggest strongly that anionic site doping may be one of the solutions to overcome the conductivity bottleneck. Now, coming to experiment, so we perform both solid state reaction, and also by thin film, okay, deposition by chemical vapor deposition technique by using some organic, for example, copper acetyl acetonate for copper source, aluminum acetyl acetonate, and thiourea dissolved in some organics. Okay, and then okay, this is actually the homemade CVD system. Only the I mean, vacuum unit was purchased from the Shanghai back. Every other part, for example, the gas introduction system and the electrode configuration, all are in-house made at our university. And you see that after a lot of effort and trial, we could find out the correct window. You know, for some CVD system, you need a large number of parameters, including the cell bias, including the electrode spacing, the substrate temperature, flow rate, composition. So many parameters has to be optimized, and finally we could find out the window in which we get the correct phase of such I mean, system by which we can generate the anionic side doping. These are the characterization results of some of the systems. As you can find, the X-ray diffraction study confirmed the correct phase formation. Not only that, you see that as soon as sulfur was introduced, there is a slight peak shift by 0.06 degree, which is expected because of the atomic radii difference in oxygen and sulfur. And you see that the sulfur dose system is having little larger strain, 0.82% compared to 0.32%. So indicating correct phase formation has been achieved. And these are the Raman and PEM results. Okay, it is very interesting. You see, if you remember that our DFT suggested some changes in the symmetry of the system. Now, the stop post B is basically a pristine SAD pattern, and the C is after sulfur incorporation. You can clearly see that the symmetry got changed, which was also predicted by DFT. Raman is also equally interesting. You see that here the Raman active mode is A1G and EG. Now in the morning we have listened to a good lecture that how to find out the number of vibrational mode, etc. And you see, if you do the irreducible representation, then you can find these are the breaking, and this EU and AU, they are acoustic mode. These two are the Raman active mode of such system, and these are the peak. The blue one is basically for the pristine sample. Look at the broad nature of the peaks, and also you can see that higher background. Now, as soon as sulfur was introduced at the oxygen side, at the anionic side, you see a number of changes, important changes. First of all, you see that both the peaks are shifted to higher wave number, and there is a significant increment of intensity, decrement of FWHM, and also interestingly, the appearance, some star mark peaks actually start to appear. Now these are because of the breaking of the local symmetry, as I already indicated, due to the sulfur incorporation. So selection rule getting relaxed, and some peaks which are otherwise forbidden started to appear. And also, for example, the background decreases. Now whenever there is a decrease in background, you can say that metallicity in the system has increased. That means higher carrier concentration have been increased. So all these actually are suggesting that actually the correct valence band dispersion have been achieved, and it should show some reflection in the electrical properties. So okay, this is the band gap measurement by simple optical UV spectroscopy. I am not discussing this in detail, so you can readily found that these are transparent in the visible region. But whether the valence band dispersion is actually achieved can also further be probed by X-ray photoelectron spectroscopy. Okay? In the morning, we have listened to a very good lecture by Professor Sharma about, initially he stated some basic of photoelectron spectroscopy. Now, I just mentioned that here, for example, the blue line is the pristine copper aluminum oxide, XPS of the surface cat, and this is when the oxygen was incorporated in the anionic site. And see, as soon as oxygen incorporated sample was introduced, you see the sulfur peak, which is, 2p half and 2p 3 by 2. And look at the oxygen peak. This is a correct chemical shift. The chemical shift actually it decreases to lower binding energy, indicating that some of the sulfur is actually replaced the oxygen. Also, it is possible to quantify how much sulfur have been incorporated in the sample. Now, to judge the valence band dispersion, we have to, place the two results, that is what is predicted from density functional theory based calculation, and also the XPS side by side. I again spent 1 or 2 minutes in this slide. For example, the uppermost panel, they indicated the density of state. This is the total density of state plot for the 3 samples. This is the pristine one, this is the sulfur incorporated one, the selenium incorporated one, and these are the partial density of state contribution. This is for the pristine sample, so you can find copper, aluminum, and oxygen. And this is for the sulfur incorporated, when sulfur is there. So now the lower panel actually represent the X-ray excited valence band spectra. You can see, okay, this is actually for the undoped system, and this one is D. This is for the doped system. So you see, just compare one thing. Look at this one. See, the copper D contribution is compared to this B picture. You can just compare the copper D contribution in these two systems. So when sulfur is introduced, so you can see that the blue line extends to more than 5 electron volt, which is also experimentally verified. Look at this. This is the copper D, the blue one. So it is about 2.8. But now when sulfur is introduced at the anionic site, it extends to more than 5. So this is a direct proof that valence band dispersion has been achieved by the anionic site doping. And if this is right, then it should have some effect on the electrical conductivity, which is clearly shown. You see the measurement of electrical conductivity over a wide range of temperature, more than 15 times increment throughout the temperature range of electrical conductivity have been achieved for such sample. Also the IV curve, by looking at it, one can say that this sample is having much lower resistivity. That means carrier density have been achieved. PL is also achieved. So this should be, a good material. And some of the conductivity bottleneck that have been, that was predicted, I explained, so that was overcome by this novel idea of anionic site doping and by valence band dispersion. So this is the paper that we published. And if somebody is interested in detail, then she can have a look. And also this has a, significantly large supporting information. There more detail can be found. But I believe this is important work because this is the first report of direct band gap Delapo site, which is obtained through this anionic site doping concept. Okay. Then we have extended this idea to other p-type systems like copper boron oxide made transparent junction by the zinc oxide nanorod with copper boron oxide system, obtain very good, for example, IV characteristics with almost ideality factor nearly equal to 1.03. So these we have reported, and we have also reported interesting electron emission from such wide band gap semiconductor. I am skipping all this part. Maybe I have left another 6-7 minutes. So I will just touch upon another aspect. How by utilizing, for example, the Raman spectroscopy, whether we can have some incidents about this whole delocalization or valence band dispersion. So I very briefly introduce to the young research scholar and the students about asymmetry in the Raman spectra. Now in the morning, a detailed lecture about the Raman spectroscopy was already presented. I'm not discussing all those parts, but this I believe was not touched. So basically, the phanoasymmetry, what is phanoasymmetry in the Raman spectrum? So you know that whenever you are studying Raman, then basically it is possible to have an interference between the intraband transition and also, I mean, the optical phonons. So these two transitions can interfere, and that will lead to, for example, the asymmetry in the Raman peak. And if you have some idea about this how this asymmetry is coming, okay, and you can theoretically formulate that what is governing this asymmetry, phanoasymmetry, then it is very interesting to have some idea about the whole dispersion and the valence band dispersion. So this is basically a discrete and continuum interference, and that gives rise to this asymmetry in the phanoresonance or the phanoresonance. Now, for this to study, we have taken another system, which is a copper chromium oxide. This is another, again, very interesting p-type material normally. And okay, we prepared this material and we introduce different set of doping. For example, we doped, first of all, of course, this pristine sample was developed without any doping, and then we introduced magnesium at chromium site. Magnesium is bivalent, chromium is trivalent, so you can expect generation on some holes. And then we introduce the anionic site doping, sulfur at oxygen, and then in another sample we introduce both cation anion simultaneous doping. So this is the DXPS, X-ray diffraction pattern. And so these four kind of sample, first of all, you have to confirm that really the correct phase formation has been taken place, and so that we have performed this detailed Rietveld analysis, and you see that the fitting is very good. With chi-square is about 1.3 to 1.4, so it's extremely good fit compared to this complex system. And we can also quantify the doping. For example, the magnesium doping percentage is 2.94 and sulfur doping is 0.84 percentage, which can be obtained from the Rietveld analysis, as you know. Now, the interesting point is that, these are optically transparent, as that can be found from this optical UV spectroscopy. You can calculate the band gap, which satisfies the criteria that it must be greater than 3.1 electron volt. Now, this is interesting, and as I just want to spend 1 or 2 minutes here. See, this is the temperature dependent Raman spectra of all the four type of samples. The leftmost upper panel, that is A, this is the pristine copper aluminium oxide, and you see that we varied the temperature from 303 to 817 Kelvin, and of course you get the EG and A1G peak, as I said. But look at the effect of temperature on the Raman spectra. Both the EG and A1G peak, they shifts to, lower wave number, lower Raman shift. So that means, thermal softening of phonon is taking place for both the modes. Okay, in case of, pristine sample. Also, as soon as we introduce some magnesium at the chromium site, you see that this shift is also increasing. I have the values of this shift, but you can find in the paper also the details about that how much centimeter inverse it has really shifted. I just mentioned the main feature of the result without going that detail because not much time is there. And also, interestingly, as soon as we introduce doping at the anionic site, you see sulfur at oxygen site, then instead of phonon softening, phonon stiffening is taking place. So that means you see here that the peaks are trying to regain its original position. And this is also, the effect increases when both are simultaneously present, both at anionic site and cationic site doping is present. Now, there is another one is this, phonon softening, stiffening part. Another is if you look at any one of these particular spectrum and take a zoom view, then you can find that I was mentioning about phanosymmetry or phanoresonance. You can find that the asymmetry in this peak are significantly affected. I'll just show, I mean, taking one spectra, maybe for the 645 Kelvin spectra, you just have a look. For example, here, you see 645K sample at the peak, and you see here that for the pristine one, okay, this is for the magnesium doped at chromium site, this is for the sulfur doped at oxygen site, and this is for the simultaneous doping. If you hit this peak with the so-called Bright-Wigner Fano function, then you can calculate this Q parameter, okay, which is called the asymmetry parameter, Q parameter, or Q is the phanosymmetry. And you see here that for the pristine sample, Q comes out to be 50. For the magnesium doped sample, Q 12.5. But interestingly, as soon as we introduce dopant at the anionic site, Q changes sign to -30, -20. This is more, I mean, clearly presented when we plot 1 by Q versus temperature. You see, as soon as there is dopant at the anionic site, the Q becomes negative. So we call this is a Q reversal upon anionic site doping, and this is a very important signature that whether we can probe the valence band dispersion through simple Raman spectroscopy. Okay. Now the rest part is some mathematical modeling. I am not going that detail about the this modeling because this will require much time. But main feature I just want to tell you that then you have seen the spectra how with temperature the peak position, that is omega Eg and omega A1G, shifts to its temperature, and then you can fit this variation of omega Eg and omega A1G with T, and then you get such type of plots, and then we can extrapolate it to find out the value of omega Eg at 0 Kelvin temperature, because that will be required for some calculation, and that you can do for both the mode, both the Eg mode and A1G mode. So that have been done. Similarly, if you look carefully, that the FWHM is also a strong function of this temperature, and FWHM is related with the lifetime of the phonon. Okay, so similarly, we can fit this type of equation with this temperature, and then extrapolate to find out the value of this FWHM at 0 Kelvin temperature, which will be required for some of our calculations. Then, using the Allen formulation of this charge phonon coupling constant lambda, it's very interesting that we can found the density of state at Fermi level. This NEF is possible if you plot this gamma, fully FWHM of Eg mode with this change in frequency or a peak shifting, or for example a 1G mode with shift in frequency. Then from the slope of these plots, okay, you see this experimental plot with the statistical variation. It is possible to calculate the density of state NEF, and it has been done. So this is basically a non-destructive technique to determine the carrier density without doing this temperature dependent Hall effect and other things by using the temperature variation of Raman spectroscopy. And there is another way to represent the data, that is you can calculate the lifetime of the anharmonic phonon and plot this product, this is the LHS product, and get a variation of this parameter as shown in the figure. And just by looking at this, you can say that whether whole dispersion has been achieved or not. So the take-home message is represented by this Feynman diagram, so that without doing any rigorous calculation, if you look at this system, say if you have localized electron hole system, okay, localized plasma, so L represents localized, that means not dispersed. And then if this is the incident frequency of the incident photon, Raman scattering, Raman probe, and this is the scatter frequency, Now, when it is localized, you have low lifetime of the phonon and you get positive Q. On the other hand, when you have dispersed electron hole system, okay, for example, here, then have high, lifetime of the phonon, you get negative Q. So just by looking at the asymmetry of the Raman's peak, Fano asymmetry to have, then it is possible to conclude that whether you have a whole dispersion system or a localized system. So this is very interesting, and this is the paper where you can find more details about this mathematical, physical modeling. And if any question, I'll glad to share. So since the time is up, okay, this electrical property was in detail investigated by admission spectroscopy also. So this result I am keeping. I just take 1 or 2 minutes more to touch upon another very interesting system, that is the P-type zinc oxide. There are lots of paper and work going on about how to achieve this P-type zinc oxide and whether they are stable or not, etc., etc. I will not touch that part, but I will just show that if you incorporate some anionic site doping in zinc oxide like chalcogen, sulfur, selenium, tellurium at oxygen site of zinc oxide, then okay, this detailed material preparation, the doping percentage calculation by detailed Rietveld analysis and phase formation that I am skipping is the detailed X-ray photoelectron spectroscopy again, confirm the anionic site doping achievement, composition calculation. But most interestingly, okay, this result I just mentioned about 1 or 2 minutes, you see that it is the capacitance versus frequency plot. This is for undoped zinc oxide. As usual, it is expected that this type of dispersion, capacitance versus frequency, you should expect. But what is unusual is that as soon as you incorporate doping at the anionic site, you see that there is a capacitance switching. That means negative capacitance is coming, okay, at some portion of frequency. Then it switch back to again positive part. And this effect is more prominent in case of selenium and tellurium doping. You see here, it starts from here, comes negative and then jumps and then follow again normal dispersion. So this is repeated, and if you think that these data are not scattered, in case of selenium and tellurium, you see that it follows some definite relaxation process, and you can fit this equation with universal Debye relaxation here and find out the relaxation process. So this emergence of negative capacitance in such system is also very unique. And okay, this is the paper. If somebody is interested, you can find more details. Of course, a lot of things can be said about this one, but I think I have taken my time. So to conclude that, first of all, I have tried to introduce to the current problem of this P-type conducting material, transparent conducting material, the so-called conductivity bottleneck. And then I discussed the valence band, engineering strategy by introducing novel doping concept also, and also by applying the orbital technique. Then I have shown that how the Fano resonance, Fano symmetry could be utilized to have some information regarding the whole dispersion in some prototype P-type system. And finally, I just touch upon the negative system. So whatever results I have shown are due to my students. So this is my group, okay, and I must thank the funding agency for their financial support. And finally, thank you all the participants and organizers for listening. Thank you all. Yeah. Mm, mm, mm. Yeah, I mean that slide is basically from Samsung. So they have not, exposed that what is their material and what is the composition, etc. But normally the data shows that it is of course more than 80% transparent. Okay, so they are saying that in future just a plastic plate, the plastic film they will use, and so that the device will become flexible as well as transparent. So that is their goal. And also in future, the computer screen will also be like that. So in that way, this transparent electronics is have great application possibilities. Okay, okay. You mentioned a very interesting question, Shailesh. The perovskite, there is a very recent article by Professor Hosono, that is perovskite transparent material, whether it's a myth or reality. So this is the title of the paper. So you see, so far my understanding goes that the problem in perovskite in making transparent conducting materials, again, yeah, in most cases it has, for example, high electronegative material like fluorine, chlorine, etc. So once the electronegativity at the anionic site is very large, then it is very difficult to get the good hole mobility. You can make it N-type transparent, but very difficult to make good P-type, transparent material with large carrier concentration. So that is the problem with perovskite. Mm. Yeah, I am here. Thank you.
Hello. Hello. Am I audible? Am
Yeah,
I
yeah.
audible?
Carry on.
Thank you. Thank you. Can you see my slides? Okay. Okay. Good afternoon to all of you, and myself Girija, and I thanks to organizing committee for giving me an opportunity to present my research work. Here I am going to present the number of layers identifications of MOS2 nanosheets via spectroscopic tools for metrological aspects. As you know, the 2D materials have received significant attention in last 1 decade due to fascinating properties and numerous applications like in energy storage device, gas sensing applications, and many more. And the 2D library covers the materials from insulator to superconductor, and the 2D TMD is having the structure of MX2 type. It is the M is the transition metal and X is the chalcogen. Here, to realize any kind of application, we measure some of the important parameters, that is the number of layers, edge structure, defects, Fermi level, and thermal conductivity. If we measure any one of these parameters by using any of the characterization technique, it can considered as a metrological technique. So MOS2 is the representative of 2D TMDs, and today keynote speaker has already discussed about the importance of spectroscopy in the phase determination of MOS2. Here we prepare the MOS2 nanosheets using the mechanical exfoliation method, and this is the schematic picture of the synthesis protocol, and this is the optical image, and this is the SEM image of MOS2 nanosheets. To further differentiate among the layers, we have calculated the optical contrast by using the image software, and here you see the CT is the contrast of the MOS2 nanosheets and CTS is the contrast of the substrate, and this profile has been captured in the rectangular region. Further, you see the contrast difference versus the layer number. From this figure, you can clearly see the layered identification by using the contrast analysis, but if you look on this one layer and two layer, there is very less difference. So further, we split this image into the three different channels, that is red, green, blue channels, and here you see you can easily find out the difference between the each layers. Now, after finding optical contrast, we perform the Raman spectroscopy, and from the Raman spectroscopy, we find there are two modes has been observed in the E1 2G and A1G. At E1 2G observed as 385 and A1G as 405. As the number of layer increases, the E1 2G shifted in low frequency direction and A1G in the high frequency direction. Further, we find the intensity ratio and frequency difference and the line width of both the parameters. On the basis of the frequency difference, it clearly depicts that the number of layers, as the number of layer increases, the frequency difference increases. So it can be one as a tool, can be used to identify the number of layers, and after to see the uniformity of these two vibrations at the different locations of the seeds, we perform the Raman mapping, and the Raman mapping with respect to this is intensity and the intensity of even 2G vibration, and this is the peak width and this is peak position, and you see the different contrast of the layers here, and in both figure you can compare, and it can very easy to distinguish the different layers. Further, the PL mapping and PL spectra has been performed to see the number of layer determination, and there are two exciton has been found out here at the 637 and 679 nanometer, and the corresponding energy values have been given here, and the valence band is splitting between the two more, the A exciton and B exciton has been shown in the table 1. If you see the table 1, there is a monotonic decrease when we go from one layer to bulk. So this value of the valence band splitting can be easy to determining the number of layers, and further we see the topography of these different MOS2 nanosheets. Here you see the thicknesses of the different layers. So the interesting thing is that this is the first time where we have got the number of layers at the one location, and the two tools, the peak frequency difference and the valence band splitting, these are the two tools which are majorly used to finding the identifying the number of layers. So thank you very much.
Yeah, I mean, have you verified your, projection? I mean, that means prediction, how many number of layers from other direct technique like say TEM or any kind of direct verification?
No, actually, we only measure the PL and Raman,
Mhm.
but not TM. We have not done.
So, how you are confirming that, okay, whatever you are getting is the right number of layers?
Okay. Yeah, we confirm from the peak frequency difference and the valence band splitting, and further supported by the AFM. We can measure the thickness of the different nanosheets using AFM.
Mhm. Okay, okay. Thank you.
Yeah, yeah, hello.
Yes, yes.
About your work, the novelty you have mentioned, the formation of different layers. Your different layers means the number of layers. It is of
Ye-
MOS2. This is what I understand. Different layers you have mentioned at one location. Now, point is that the Raman is your proving what is the diameter of that beam, and how do you distinguish between the two stops? Suppose if you are doing the mapping, and
Okay,
it is a continuous mapping. So what about the overlap locations?
okay. So if you see the optical image and the you talked about the beam diameter, here we using at the 50x magnification, and the 1 micron is the spot size. And if you see this optical image and this location here, at the edge of these two layers of MOS2, so there is a difference of the substrate. So we only choose this layer for only where the layer has been sitting on the substrate, not behind this one.
Okay,
Hello.
yeah. So this is you checked with how many samples. Basically, the it is your metrological aspects you have mentioning.
Okay.
So at the one point, the number of times you have measured, and did you find any difference in your mapping?
In different samples.
I suppose for the same samples, if you
No, actually mapping has not been performed and repeated time, but
Hmm.
we measure the spectra at the different times. So it almost same, but not the mapping we have not performed at repeated time.
Okay. Okay, that's all from my side. Thank you.
Okay.
Girija, you have performed AFM. Are you
Okay.
aware of how AFM is calibrated, atomic force microscope?
No, actually, ma'am, I don't know about this.
Okay. Then another question. When you say you have done repeated measurements at different times, so what was the purpose and what did you do with the scatter of data? Because it may not be the same reading all the time. So what did
Okay.
you do about it?
Yeah, actually, there are some differences, but when we perform the Raman spectroscopy, so the repeated measurements show about the 1 centimeter inverse difference between the two in the repeated measurements in each layer.
Okay.
We have
One
performed only
centimeter
three times,
difference.
three
No, one
times.
centimeter difference between two readings. Like for
Yeah,
example, one reading
in
came
the
this much
in the
and another
range
reading
of
came.
in the range of 1 centimeter, not more than that.
So 1 centimeter is how much percentage of your reading?
Actually, yeah, this is very low, but it can be tolerable in this Raman measurement, I think, for peak position.
So did you calculate standard deviation or you are saying the full range deviation?
No, no, we calculated only the full range deviation, not the standard deviation. And here you see is the 5% of here you see if you see the error bar on the peak width and the intensity ratio, so it is the 5% of standard deviation.
Okay.
My slide is visible. Good afternoon, all of you. Myself, Prince. I am going to present a research abstract on terahertz generation in topological insulator. First of all, I would like to give you a brief about topological insulators. Topological insulators are quantum materials that have insulating bulk, but it is conducting at the surface. Topological insulators are different from insulator because of this surface state. In insulator, there is well-defined band gap. In insulator, there is well-defined large band gap as shown here, and the electrons orbit with the cyclotron frequency in it. The concept of topological insulator come into picture with the discovery of quantum Hall effect, in which in a 2D system, when there is large magnetic field applied in it, the electrons start orbiting around it, but the electrons at the edge of the 2D system does not complete its orbit and start skipping. Therefore, this skipping orbit give rise to a edge state. Yes, sir. Oh, wait a second, sir. Okay, sir. Wait a second. Now it is the third slide. It is the third slide. Okay, sir. So I will start with the insulators. In insulator, there is well-defined large band gap as shown here, and the electron orbits with the cyclotron frequency in it. The concept of topological insulator came into picture with the discovery of quantum Hall effect. Quantum Hall effect observed in 2D system, in which when a strong magnetic field is applied, the electrons or the charge carrier start oscillating. As in insulator 2, but the electrons at the edge of the 2D system, that is shown here, does not able to complete its orbit and thus forms skipping orbit, which led to formation of edge state in between valence band and conduction band. Similarly, in spin quantum Hall effect, because of the spin up and spin down, there is formation of bidirectional skipping mode. That is, this movement and another spin up movement is in this direction. Because of this, it leads to a dual edge state as shown here. In TI, similarly in TI, which is a 3D system, this state form a dark cone-like structure which led to the surface state in the system, while the intrinsic spin-orbit coupling will work as an external magnetic field. For in case, in quantum Hall effect, there is need of strong magnetic field, while similarly in spin quantum Hall effect, there is need of external strong magnetic field. While in topological insulator, the strong magnetic field is intrinsically present in the system because of spin-orbit coupling. As my topic is terahertz generation in TI, terahertz is a band of frequency from 0.3 to 3 into 10 to the power 12 hertz. This frequency has numerous applications which include medical imaging, screening, communication, astronomy, quality assurance, and etc. In my experiment, we detect the terahertz in Ti using transient absorption ultrafast spectroscopy, in which Ti, which is placed in a place of a sample, is excited by 650 nanometer with an average power of 1 milliwatt. The kinetic profile which comes out through this experiment is considered, which show oscillation in 1 picosecond to 10 picosecond range. These kinetics are analyzed using this given process, and we term this process as filtered high frequency component followed by fitting data. In this process, we extracted the fast oscillation which is between 1 picosecond to 10 picosecond, and using the high pass Fourier filter, we filter out the oscillations from the decaying profile of the charge carriers. These filter oscillations are then fitted with the sine damp function, and the fitted data give us a frequency which lie in the terahertz regime in case of a topological insulator. In our experiment, we take 3 Ti, which are Bi2Sc3, that is bismuth selenide, Bi2Te3, that is bismuth telluride, and Sp2Te3, that is antimony telluride. These are the 3 single crystals that are grown in our lab. The oscillations that are fitted in case of Bi2Sc3 is shown here. Okay, sir. These oscillations are given here, while in case of Sp2Te3 is this, and in case of Bi2Te3 is this. The terahertz that comes out through these oscillations are 2.11 terahertz in case of bismuth telluride, 2.42 terahertz in case of bismuth selenide, and in case of antimony telluride it is 1.94 terahertz. This is few references, and thank you. Any question?
Yeah, how do you confirm that your samples, that is Vi2Te3 or whatever you have used, are really topological insulator?
Sir, there are various other measurements that are done using the PPMS, that is physical property measurement, and there we find we fit the MR percentage with the HLN and modify HLN equations, and that give us a hint that the crystals that are formed are topological insulators.
So that means you said from MR measurement you can confirm.
Sir, we can get a hint that these are.
And your sample, are they polycrystalline or single crystalline?
Sir, these are single crystal, and we confirmed that using XRD. I'm not showing that XRD data here.
That's okay. Then if you take the single crystal, then I think depending on orientation, so of the sample with respect to the probe beam, did you get some change of the terahertz frequency or polarization state? Or have you observed such kind of thing?
Sir, this is a single crystal, therefore the planes lie in one direction. So I tried.
But you can change the orientation.
So I tried various other experiments by taking different mechanical flakes, but the terahertz frequency lie between 2.42 to 2.61 in case of bismuth selenide. So there is slight change, not that much change with the different flakes or orientation.
Okay, from my side it's okay.
Yeah, about your experimentation, basically using crystals, which you mentioned is a single crystal, you have generated terahertz frequencies.
Yes, sir.
Yeah. Now, these frequencies are very close to the value you have measured. How you can get it confirmed? Means it's a very close 2.11 or whatever you are mentioning, 1.9, 2.42. So, because what you in the one of the slide you have mentioned that you have used it in a way to filter out the high frequency. So high frequency means more than that frequencies you filter out. That is also coming out in your experimentation. So this is a little confusion to me. So can you clarify it? And my question is basically how you can assure about these frequencies you have generated.
Okay. So I start from the back.
Yeah.
Firstly, how to assure that these are the frequencies that are coming out. So we done the terahertz spectroscopy using Bi2SC3, that is bismuth cyanide crystal, and we get the same terahertz, that is we get 2 terahertz from that study also.
I mean, is there some reference sample you have?
No, sir. These sample I made by myself in my lab.
And then you also use a reference sample for it. Yes, this same frequency is coming. Means.
No, sir. That sample, मतलब कि हमने बार-बार बनाया है, तो फिर half of the sample I will use in my ultrafast and half we send for the terahertz spectroscopy, and then we confirm that that whatever results we are getting from the ultrafast spectroscopy are confirmed from the terahertz spectroscopy too.
Okay, fine. So now the second question. It is means basically topological insulator. Yes, that was also the previous jury has asked about confirmation of that, whether that is a topological insulator or not, or if it is that, up to what extent it is. That is also the second question comes. So now, did you feel some relation can be established between the the quality of topological insulator or something, how much it is giving your topological insulating property with your generated terahertz frequency from that crystal?
Sir, this is my future study that we are trying to dope the crystal with different materials so that to disturb the topology of the system. For in case if I dope the system with the magnetic doping, the Racon will be disturbed, and therefore we will get some change in the terahertz or not. This is my future study and I'm working on it. So for today, from now I don't answer that, but in future hopefully maybe I can.
Okay. Okay. Thank you. From my side it's okay. Over now. Yeah.
Thank you.
Prince, can you go to slide number 6?
Now it is slide number 6?
Yeah, slide number 6. Yes. So when you are using this transient absorption ultra fast spectroscopy, what is the role of when you put this second item on this thing?
Which one, ma'am?
You have not this thing. Initially you are using laser. Then what is the second block diagram? Can you explain what is happening here?
Ma'am, second block diagram. First is a micro model of laser. Then there is an amplifier.
Yeah.
Then there is beam splitter. Then there is optical parametric amplifier, that is I named as toppers.
Yeah.
So you are asking what toppers?
इसका function मैं आपसे पूछ रही हूँ.
अच्छा. So ma'am, basically toppers help us to get the desirable wavelength. As in case of a model of laser, we get 800 nanometer wavelength laser, pulse laser, which we can tune using the optical parametric amplifier, where the second harmonic generation, third harmonic generation.
ये तो बता दिया, उससे क्या मिलेगा? What is an optical parametric amplifier? What is its role?
मैम ये वेवलेंथ सेलेक्ट कर रहा है ना मेरे लिए, मीन्स मैं 800 नैनोमीटर का जो यूज कर रहा हूँ. अभी मैंने बोला था कि मैं 650 नैनोमीटर यूज कर रहा हूँ पंप करने के लिए, तो 800 नैनोमीटर को फॉर डिजायरेबल एंगल्स आल्सो मैकेनिकली और यूजिंग द क्रिस्टल्स वो ट्यून करके मुझे 650 नैनोमीटर प्रोवाइड कर रहा है.
ओके,
तो ये एक तरह से
fine. And then the second thing is, when jury was asking about the frequency difference, you said you got slight difference. So
yes,
how, I mean slight difference तो ठीक है. अब आपने वो slight difference का क्या analysis of variance किया? Did you do many samples? How did you do analysis of variances? Because you got slight difference, whatever you say, it is a variance. So how did you do analysis of variance? What is the reason for this variance?
Ma'am, basically I got three samples of bismuth cyanide, and in all of three I take two pieces of the crystal, the single flakes, and then we repeat the same experiment. For the same experiment
3x2 मैट्रिक्स बना के आपने किया है.
अब मैंने उतना नहीं किया है कि एक्जेक्टली देखने के लिए, बस मैंने किया 3 सैंपल्स का.
That is fine. What experiment you have done is fine. 3 you
Okay.
have taken, then 2 2 you have taken. Okay.
Yes, ma'am.
Now, what I am talking is whether you done the study that is the difference within and between the samples. Within will mean that between the two of same, and then these three. So, is it different, significant difference between within the sample and between the samples?
Ma'am, there is no difference basically within the
तो
sample.
सिग्निफिकेंस स्टडी किया है, स्टैटिस्टिकल कैलकुलेशन किया है, दैट इज व्हाट
मैम
आई एम
कैलकुलेशंस वगैरह नहीं किए हैं.
नहीं किया. दैट्स द सिंपल आंसर.
Okay.
हाँ, बी सिंपल एंड स्ट्रेट. इफ यू हैव नॉट डन,
ठीक
प्लीज थिंक ऑफ डूइंग दैट. ओके,
है.
because any claim if you are making, it should be backed up with a statistical analysis of areas. Okay.
ठीक है. मैं फिर ये आगे स्टडी में कर लेता हूँ.
Thank you, sir.